All right, if you're tackling your GCSE Physics revision, you are in exactly the right place. In this explainer, we're going to dive deep into the AQA section on atoms and nuclear radiation. We're going to break this all down so you can walk into that exam feeling totally ready to go.
So here's our game plan. We'll kick things off with why atomic nuclei are unstable in the first place. Then we'll check out the different types of radiation they spit out. After that, we'll get into how to write the nuclear equations for all this, get a really solid grip on what half-life actually is, and finally, we'll clear up that classic confusion between contamination and irradiation. Let's jump in.
Okay, first things first, let's get right to the heart of it. Why does radiation even happen? Well, it all starts with a problem, an instability right at the very core of an atom. So what is going on here? Well, you know the nucleus is just jam-packed with protons and neutrons. And for that nucleus to be stable, it needs a really specific, happy balance between them. In some atoms, though, that ratio is just off. Maybe there are too many neutrons, or maybe too few. Sometimes the nucleus is just too big and heavy overall. And this imbalance, this is what creates an unstable nucleus that's basically just waiting to change. And that change, that's what we call radioactive decay. Now, this is the official AQA definition, so you want to pay close attention to the keywords. Random is huge. We can't predict when any one single nucleus will decide to decay. And more stable, that's the whole point of the exercise. The nucleus is just trying to chill out, get to a lower energy state, and it does that by throwing out some particles or energy as radiation.
So now that we know why they decay, let's look at what actually gets sent flying out in the process. There are 4 types of radiation that you absolutely need to know for your exam.
Here they are, the big 4. You've got the alpha particle, which is basically a helium nucleus, 2 protons and 2 neutrons all bundled together. Then there's the beta particle. This one's interesting. It's a super fast electron that's actually created inside the nucleus when a neutron changes into a proton, and then it gets kicked out. Gamma rays are the odd one out. They're not particles at all. They're a blast of high-energy electromagnetic radiation. Think of them like superpowered X-rays. And last, sometimes a nucleus just decides to eject a single neutron.
Okay, this slide is absolutely crucial. Comparing these properties is a classic exam question, so let's lock it in. Alpha particles are big, they're heavy, they're highly charged. This means they bump into everything, which is why they're so easily stopped, even by a sheet of paper or your skin, and they only travel a few centimeters in air. But all that interaction makes them highly ionizing. Now, beta particles are much smaller, much faster. They can zip through about a meter of air, and you'll need a thin sheet of aluminum to stop them. Their ionizing power is kind of in the middle. And finally, gamma rays, pure energy. They are incredibly penetrating. You need thick lead or concrete to even slow them down. But because they don't interact much, they're the least ionizing of the 3.
Right, so we know what decay is and what it shoots out. Now let's look at how physicists actually write all this down. Think of it as the special language they use to describe exactly what's happening inside that nucleus.
Just like with chemical equations, the big rule here is that everything has to be balanced. But we're not balancing atoms. Here, we're balancing the mass number, that's the top number, and the atomic number, which is the bottom number. The total of the top numbers on the left has to equal the total on the right. Same for the bottom numbers. Simple as that.
And this makes it so easy to remember the rules. For alpha decay, the atom loses an alpha particle, which, remember, is 2 protons and 2 neutrons. So its top number, the mass, goes down by 4. And its bottom number, the proton count, goes down by 2. Easy. For beta decay, a neutron turns into a proton and spits out an electron. Since a neutron and a proton have basically the same mass, the top number doesn't change at all. But you've just gained a proton, so the bottom number has to go up by 1.
Okay, we've said that decay is totally random for any one atom. But what happens when you have billions upon billions of them all together in a sample? Well, that's where half-life comes in. It's this incredibly powerful idea that lets us predict how the whole group will behave over time.
So here's the textbook definition, and notice you can say it in 2 ways, and both are totally correct. You can talk about half-life as the time it takes for half of the unstable nuclei in your sample to decay, or you can think of it as the time it takes for the activity, the number of clicks you'd hear on a Geiger counter, to drop by half. They both mean the exact same thing.
I know, we keep coming back to this, but it's such a fundamental point. Half-life does not tell you when the next nucleus is going to decay. That's impossible to know. What it does tell you is that if you wait for a certain amount of time, you can be very sure that half of your original sample will have decayed. It's all about statistics and probability when you're dealing with huge numbers.
And this chart just shows it perfectly. Let's say you start with 100% of your radioactive stuff. You wait for one half-life to pass, and boom, you're down to 50%. You wait for another half-life, and that gets halved again, leaving you with just 25% of what you started with. After a third, you'd be at 12.5%, and so on and so on. A key thing to remember is that, theoretically, it never actually hits zero. It just gets smaller and smaller forever.
All right, on to our final section, and this is a big one because it deals with a really common point of confusion that trips people up in exams all the time. What is the actual difference between contamination and irradiation? If you can get this straight, you can pick up some really easy marks.
This table really lays it all out. Let's start with irradiation. That's when you're just exposed to radiation from a source that's outside your body. Think of a medical X-ray. The rays pass through you and then the machine is turned off. You are not radioactive. The danger is gone. Contamination, though, is totally different. That's when the radioactive material, the actual radioactive atoms, get on you or inside you, like getting some radioactive dust on your clothes. Now the source of the radiation is stuck to you, constantly decaying and beaming radiation right at you, up close. That's a much bigger problem.
So this is the absolute key takeaway. If you remember one thing, make it this. An irradiated object is not radioactive. The danger stops when the source is removed. But a contaminated object is radioactive because the source of radiation is now physically on it or in it. That is the critical difference.
Okay, to pull everything together, here's a classic exam-style question to get you thinking. We know gamma rays are super penetrating, and we know a short half-life means the stuff decays really quickly. So, why do those two properties make a substance the perfect choice to use as a medical tracer that you actually put inside someone's body for a scan? Have a think about how you put all the pieces together for that answer. That's all for this revision session. You've got this. Good luck in your exams.